Hey everybody, welcome to chapter 12. We're going to be talking about one sample z-tests, which we've already done a bit of, as well as one sample t-tests, and what's the difference and when would you use one over the other. Let's dive in. So oftentimes what we like to do in statistics is to compare different groups in terms of their means, their average on some variable or variables of interest. So for instance, what if we wanted to compare the average height of Denver Nuggets players to just the average height of the general population and see if those things are very different or very similar? What if we wanted to compare average salaries of people with a bachelor's degree versus a master's degree versus a doctorate? What if we wanted to compare average reading scores or reading comprehension scores on an exam before and after a group of children participates in some kind of reading program? Or we could compare the average exam score of our class to the average exam score of another section of the same class. There's all kinds of things in the real world that we would like to compare in terms of averages. And there's a lot, I mean a lot, and we're going to go through them all, a lot of different statistical tests that will help you compare the means of two or more groups. This chapter focuses on one sample z-tests and one sample t-test, which we'll talk about in a second. There's also independent samples t-test, paired samples t-test. There's one-way ANOVA, there's factorial ANOVA. There's a lot of different kinds of statistical tests that we can employ to help us compare averages of some variable, either before and after some event or between entirely separate groups. So when do we use one sample z-test and one sample t-tests? This is specifically when we want to compare a single sample's mean against the mean of an entire population. Okay, so for example, if we want to compare the average GPA of our class, which is just one sample of students, against the average GPA of all CU students, which is the population of students, then we would want to use either a one sample z-test or a one sample t-test. Also, if we want to compare the average 100-meter sprint times of a sample of elite athletes, so one sample of elite athletes, to the average sprint time of people in the general population, that also would require a one sample z-test or a one sample t-test. But how do you know when to use a one sample z-test versus a one sample t-test? Well, the main difference for our purposes is when it comes down to whether you know the population standard deviation or not. Okay, so in the case of one sample z-tests, if you know the standard deviation of the population, you can do a one sample z-test. That has a normal distribution, a z-distribution. You don't need to worry about degrees of freedom. You calculate it with standard error, which we've talked about before. We'll touch on that in a second. Don't worry about this proportion testing row. Not too interested in that part. Now, for a one sample t-test, which we have not done before, you use this when the population standard deviation is unknown. Then we have to use a different distribution. Instead of a z-distribution, we're going to use a t-distribution. You do need to know the degrees of freedom. And instead of the standard error, it's now going to be using something called the estimated standard error. Here's a handy flow chart. You can see that the very top of this is asking whether we're comparing means or we're testing for relationships. The right side of all of the flow chart is about mostly Pearson's R, which is correlations, and regression tests, and it also has a chi-square, which we're not going to talk about in this class. But all of the left side of this flow chart is based around comparing means, which is a huge part of statistics. And then the next part of the flowchart says, how many sample means are we talking about? Well, for our purposes, there's only one sample mean right now, and we're comparing that one sample mean against the population mean. And so we go down the flow chart to the left that says 1 sample mean, and then it asks us, is sigma known? Is the population standard deviation known? If the answer to that is yes, you do a 1 sample z-test. If the answer to that is no, you do a 1 sample t-test. So in a 1 sample z-test, you've got to know a number of pieces of information. You've got to know the population standard deviation, you've got to know the sample size that you have taken, and that'll allow you to calculate the standard error. So we've seen this slide before. The standard error is basically the standard deviation of the distribution of sample means, and it represents an estimate of sampling error. All right, let's get some practice finding the standard error, also known as the standard error of the mean. So you're interested in the average amount of time people spend on social media. You get 36 people in a sample of undergraduates. You know that the average time all undergraduates spend on social media is 2 hours per day with a standard deviation of 0.5 hours. What is the standard error of the distribution of sample means? Well, if you use the formula from the previous slide, the standard error equals the standard deviation of the population divided by the square root of your sample size. So you would take 0.5 hours, which is the standard deviation of the population, and you would divide it by the square root of 36. If you figure out the math on that one, should be 0.08. So C is correct. Okay, so remember now, the reason why we can't just use a simple z-score transformation like we used to do was that involved just looking at a single person's z-score compared to the mean of the sample or the population that it came from. But now we're talking about comparing a sample mean to the population mean. So now what we're actually trying to do is compare the mean of a sample of whatever group of people we're interested in measuring to the mean of a population. So the proper comparison distribution in this case isn't a distribution of individuals or individual scores. The proper comparison is a distribution of means. It's an entire sampling distribution that is made up of many different sample means. So we're comparing one sample mean to a distribution of sample means, basically. And that is called the sampling distribution of sample means, or just the distribution of means. So real quickly, again, there's like 3 different distributions that we're talking about right now in a 1 sample z-test. There's the original population that our sample comes from, right? If we're talking about our class and we're looking at the class's GPA versus the overall GPA of all CU students, the population is all CU students, right? And then our little sample would come from that population. But in between the population and our one individual sample is the distribution of sample means. And basically that would be formed by taking many different samples of a particular size from the population and then plotting each of the means of all of those hypothetical samples. Now you don't have to actually take hundreds or thousands of samples from a population and then plot all the means for each of those samples. You can do it hypothetically. If you already know, for instance, the mean of the population and the standard deviation of the population, which we would if we were looking at GPAs of all CU students, because we know that we actually can look at the GPA of all CU students and find the mean and find the standard deviation. If you can do that, you also can instantly know the mean and standard deviation of the distribution of means, because the mean of the original population is the exact same as the mean of the sampling distribution of sample means. The standard deviation of the distribution of means is equal to the standard deviation of the original population divided by the square root of your sample size. And that's standard error. We just saw that on the previous slide. So let's take an example for the one sample z-test. Let's say you've got a group of students in a class that has online quizzes. Okay, and the online quizzes are supposedly to make them do better on exams in class. We're going to compare the average exam scores of that one class to the average exam score of an entire population of students from all other classes that do not have online quizzes. Okay, so basically we're trying to say, is the class that has online quizzes, do they do better overall on their exams than all of the population, the average population of students that does not have online quizzes in their classes? Okay. So the null hypothesis would be that, in fact, online quizzes do not have an effect on average final exam scores. In other words, the mean final exam score for the particular sample, the class that has online quizzes, is not significantly different than the mean final exam score of classes that don't have online quizzes. Okay? The alternative hypothesis would be that online quizzes increase the final exam grade of the students of this particular class compared to the average exam grade of all of the classes that didn't have online quizzes. So in actually conducting a one sample z-test, we've done this one before. Let's say, for example, that we've got average exam scores from a current statistics class that has online quizzes. And we're trying to compare that average exam score of this one class that has online quizzes versus the average exam score of an entire population of classes that don't have online quizzes. Okay, so what we know, the statistics and parameters that are given are, we have a population mean of 75. That's the average, the population average exam score. That also has a population standard deviation equal to 3 points on exams. Then, when we compare our single sample to that, our sample, which is a class of students who take an exam, and that class also has online quizzes as a way of trying to boost exam scores. And it looks like the sample mean, which is the average exam score for this particular sample of students, X bar, is 82. That's pretty high. It's a very high average. And there's 30 students in our sample, n equals 30. Okay, so once you have all these pieces of information, you can find a z-score. And this is actually a z-score for the sampling distribution of sample means. Okay, it's not just a distribution made up of raw scores, it's a distribution, a z-distribution of means, made up of means. And we can figure out where our sample mean falls within that distribution of means. So you take the sample distribution, you take the sample mean, 82, X bar, and you subtract that, you subtract the population mean, mu, from that. Okay, so you're finding the deviation basically from the sample mean and the population mean. And then you divide that by the standard error of the sampling distribution of sample means. So to find the standard error, that is population standard deviation divided by the square root of sample size. So in this case, we have all those numbers already. We would plug in 82 minus 75 divided by the standard error is 3 over the square root of 30. If you work out the math, you get a z-score on the distribution of means of 12.73. And then we could do one of two things. On a z-table, you could try to look up, well, what's the probability, what's the p-value of seeing such an extreme z-score of 12.73? The table doesn't even go up that high. So there's essentially zero chance that you would see this. That means it's significant because the p-value is going to be less than 0.05. The other way you could look at significance is to compare this. If you knew if it was a one-tailed or a two-tailed hypothesis, you could compare a z-score of 12.73 to whatever the critical value is, depending on if you have a one-tailed or a two-tailed test, which is going to be either 1.64 or 1.96. 12.73 is like way, way higher than any of those things. So it's definitely going to be significant, and it's going to be in our rejection regions. So again, from that previous example, we found a z-score of 12.73, which like I tried to put that kind of on on this diagram way, way, way to the right. That is definitely going to be a p-value less than 0.05, and it's going to be in the critical region. It's just so massive, right? If you were to look up the critical z-scores associated with the two-tailed test, you'd find a z-score of negative 1.96 and also positive 1.96. If you were to look up the critical z-score associated with a one-tailed hypothesis or one-tailed test, it would be 1.64. So obviously 12.73 is like way more extreme than all of those numbers in the positive direction. So it's going to be a significant difference. The hypothesis here would be there's a significant difference in the average exam score of the sample of students from the class with online exams, or rather online quizzes, versus the average exam score for the population of students that don't have online quizzes. All right, let's use a new example. All right, so let's say that you and your friends want to know if you're studying enough, if you're studying as much as other people in your major, for instance, right? So you find a little sample of your friends and you ask everybody, including yourself, how many hours a week do I study? And you find that you and your friends study on average 4 hours per week, and that has a standard deviation of 1.2 hours. Then you look up and you find the average study time of everyone in your entire major is 5 hours per week. Okay. You don't know what the standard deviation is. And you think, all right, I'm going to try to use a one sample z-test to compare myself and my friends' study time to the overall population study time. But we've got a big problem here, because in a one sample z-test, you have to figure out what the standard error is, the standard error of the mean, which is the standard deviation of the sampling distribution of sample means. You can't figure that out if you don't know the population standard deviation. So that puts us in a little bit of a bind. We're not going to be able to use a one sample z-test to figure this out. So what are we going to do? Well, it turns out for a one sample t-test, which we're going to be doing in this chapter, you don't actually have to know the population standard deviation to calculate standard error. We're going to calculate something similar, but a little different. It's called the estimated standard error. And why is it estimated? Well, in the case that you don't actually know the population standard deviation, which is a lot of the time you don't know what the entire population standard deviation is, we actually use our sample, our single sample standard deviation to estimate that standard error. So we're actually, instead of using the population standard deviation, we use our sample standard deviation. So you can see that equation up at the top. Now we're going to have the estimated standard error, which is represented by just the letter S, subscript x bar, equals S, that's the standard deviation for our sample, divided by the square root of our sample size. So in this case, you're still trying to compare the mean of your sample to a population mean. But now you don't know the population standard deviation, so we're going to have to estimate the population standard deviation with the sample standard deviation. That means we have to use a t-distribution, not a z-distribution. You have to use a t-distribution if you don't know the population standard deviation. So now we have our original population, which is a bunch of people and all of them in your major who study X amount of hours per week, right? The comparison distribution is no longer going to be a sampling distribution of sample means on a normal distribution or a z-distribution. It's actually going to be a t-distribution of sample means. So it's still a distribution made up of sample means, but because you have to estimate the standard deviation, now using your sample standard deviation, the estimated standard error, which actually is the standard deviation of this t-distribution of sample means. Let me say that again. The standard deviation of the t-distribution of sample means is the estimated standard error, S sub x bar, okay? And how you find that is standard deviation of your sample divided by square root of the number of people in your sample. So we are trying to compare our sample mean, hours studied per week, against all of the other people's in our major, all of the other student in our major's average study time per week. But we have to estimate the standard deviation of this t-distribution of sample means now, and therefore the shape of it becomes a little wonky. It's not perfectly normal usually, except for in the case when we have large sample size, which you'll see on the next slide. And when I say the t-distribution, I'm really talking about the t-distribution of means, as opposed to like the z-distribution of means, which we've been talking about in the last chapter or two. The t-distribution differs a little bit. You'll remember the z-distribution was always normal if the original population was distributed normally, or if you had sample sizes of 30 or more. The t-distribution is pretty similar in that lower sample sizes are worse. They mean that the distribution of means for a t-distribution is not normal unless you get higher numbers of people in those samples. So the larger the sample size, the more normally distributed a t-distribution of means will be. And you can see that in the diagram on the upper right here. The bottom distribution, if you have degrees of freedom equal to 10, which means 11 people in your sample size, because degrees of freedom is n minus 1. So if you had 11 people in the sample, that's not a very normal looking distribution because it's got these really fat, thick tails on the side, and it doesn't have as nice of a peak in the middle, even though it is symmetrical. Then if you increase degrees of freedom to 30, so that'd be 31 people in your sample. It's getting more normal, but it's still not really normal. Then we got a sample size of 51, so that's the degrees of freedom of 50. That's looking pretty normal at that point. So the thing I want you to take away from this is having more people in those samples is going to better approximate a normal distribution for the t-distribution of means. And I want to note again that the degrees of freedom for a one sample t-test is n minus 1. So far in the class we've been talking about converting correlation coefficients into t-scores and then comparing them to t-critical values using a degrees of freedom of n minus 2. But this particular test, the degrees of freedom for a one sample t-test is just n minus 1. And that's because you're only using one single variable from one single sample. In correlation, you have two different variables that you're worried about. So here, we're just worried about one single variable, one standard deviation, and it's going to be degrees of freedom of n minus 1. One of the consequences of the t-distribution of means being differently shaped, like having these really fat tails, is there's a lot of the proportion of the entire curve, meaning there's a lot of sample means in those tails. That's a problem because it actually means that the critical regions will be further to the extremes, they'll be further to the sides of those tails, meaning that it's actually harder to get a statistically significant result. Like you'd have to get a larger mean for it to still show up in that critical region where we can reject the null. So it's actually much better to get, again, higher degrees of freedom, higher sample size, so that it becomes a bit easier to reject the null hypothesis if you're looking for, significant differences between two different means. All right, so let's actually move on with our example and talk about how to conduct a one-sample t-test. So let's state our hypotheses first of all. The null hypothesis is that you and your friends study the same number of hours on average as everyone in your major. But the alternative hypothesis that you've come up with is that you and your friends actually study less than average compared to people in your major. Also notice that the alternative hypothesis is a directional hypothesis, which means later on we're going to be wanting to look up the critical t-value for a one-tailed test. You had collected your data earlier and you found that study hours for sample of you and your friends is a mean of 4 hours per week with a sample standard deviation of 1.2 hours per week, and you collected a total sample size of 12 people. Meanwhile, the population study hours per week for your major on average was 5 hours per week that you looked up in some kind of online brochure of the department. Now, finally, we get to calculate our t-statistic. This is very similar to the z-statistic, but again, we don't use the standard error. We're actually using an estimated standard error, which is this bottom term, s over the square root of n. So to calculate this is for a one-sample t-test. The t-score, t-value, or t-statistic, all those things mean the same thing, the lowercase t, equals the sample mean minus the population mean divided by the sample standard deviation over the square root of the sample size. So if we plug in all of our values, we've got t equals, this is the observed t, equals a sample mean of 4 minus population mean of 5 divided by sample standard deviation of 1.2 over the square root of the sample size, which is 12. If you do the math, you get an observed t-score of negative 2.89. So the next thing we need to do is figure out, well, is that value, negative 2.89, that observed t-score, is that significant? Meaning, do we reject the null hypothesis that in fact there's no significant difference between our sample mean and the population mean? If we get to reject that null hypothesis, it means that there in fact is a difference in study hours, average study hours between our sample and the overall population. So we got to figure out if our observed t-score is more extreme than a critical t-score that we have to look up in a table. How are we going to do that? Well, we know that our alpha level is going to be 0.05, and we had originally a one-tailed test or a one-tailed hypothesis because we did have a specific directional alternative hypothesis. So we're going to look up a t-value, critical t-value, for a one-tailed test with degrees of freedom of n minus 1. Remember, for a one-sample t-test, degrees of freedom is n minus 1. Since we had 12 people in our sample, minus 1, we're looking at a degrees of freedom of 11. So we find the row for the degrees of freedom equal to 11, and the column is going to be a level of significance for a one-tailed test of 0.05. And if we go to where the row and column meet, we find a critical t-score of 1.796. Now remember, since we're interested in actually the lower end of the t-distribution because we think that maybe we study as a group less than everyone else in the major on average, we're actually interested in the negative 1.796 as the critical t-score. Okay, now we're going to compare our observed t-score to the critical t-score we just looked up. The observed t-score, remember, that's the t-score that actually represents the difference in average hours studied per week between our sample and the population. That's the t observed. And we found an observed t-value of negative 2.89. We're going to compare that to the critical t-value we looked up in the table of negative 1.796. If you draw this out on an example t-distribution, first of all, you'll notice that with the degrees of freedom of only 11, that's a really small sample size. The t-distribution here has really thick tails. It doesn't look quite normally distributed, even though it's symmetrical. It has very thick tails, which actually means there's more of the distribution in the tails, and that pushes the critical t values further into the tails, and so it's actually harder to get a significant difference in means here. But anyways, we can see if we draw the critical t-score of negative 1.796, that sets up the critical region. Now, if our observed t-value falls within that critical region, we get to reject the null hypothesis. And in fact, that's what we see, right? Negative 2.89 is more extreme than negative 1.796. It falls inside the critical region, and therefore we get to reject the null hypothesis. You also know, because the y-axis of this t-distribution is probability, that the further you go out into the tails, the lower probability you actually have of finding a statistic in that region if the null was true, because remember, this t-distribution actually represents the null hypothesis. So a score of negative 2.89 is actually very unlikely we would see such a extreme t-score if in fact the null was true, meaning that if in fact there was no significant difference between the sample mean and the population mean. If the null was true, but because there's such a small percentage likelihood that that's the case, and you know that because we're further out into the tails and we're in fact beyond the critical cutoff region marked by the t-critical value, we know that the p-value, the probability value of observing such an extreme statistic if the null was true would be less than 0.05, which also means it's a significant difference in terms of our sample mean compared to the population mean. Overall, we can conclude that the alternative hypothesis is correct, and that, unfortunately, we are not studying as much on average as everyone else in the major. All right, we made it through another part, and I love this meme. Mr. T-test, I pity the fool that doesn't know their population standard deviation. And that is exactly why we had to conduct a one-sample t-test as opposed to a one-sample z-test. All right, I'll see you in the next video.